Hey, welcome to our first live demonstration of the MP-1. We're still getting used to it. Hopefully you guys can hear the audio okay. So you're in our demonstration corner, which is a part of our laboratory. And we're here to talk a little bit about the MP-1, but I thought we'd turn the camera and just talk about the other equipment that's in the demonstration corner that we will talk about in future live demonstrations. So if we turn to your right, this is the GHFM-01 Garda heat flow meter. This makes measurements of heterogeneous and layered materials, somewhat complex, measures the resistance via ASTM E1530, and that goes up to 300 Celsius. This is our heat flow meter, which we have in a variety of sizes and shapes. This measures insulative materials and construction materials via ASTM C518 and related international standards. And if we go over here, we have our THWL1 or transient hot wire. This is a primary measurement for liquids following ASTM 7896. This goes up to 200 and 300 degrees depending on the model. It measures thermal conductivity, diffusivity, and specific heat. The key being that you can back pressure your sample up to 20 and 30 bar, which allows you to measure past boiling points. This is our basic transient plane source, TPS2, following ISO 22007-2. This can be scaled between insulative 100 watts per meter Kelvin, and it can be maxed up to 500 watts per meter Kelvin. So it was the combination of these two popular models that are primary measurements for liquids and solids, pastes, and powders that was really the inspiration for the MP-1. So we combined them and brought them together as the MP-1 and added some more technology to maximize the versatility of the instrument. So the MP-1 actually, MP-1 stands for measurement platform. We combined three methods. Transient hot wire, so this is a transient hot wire room temperature sensor. This is what you would get if with a room temperature configuration. So room temperature configuration means that you just have the controller itself. We'll talk more about these two devices later. So this is a transient hot wire sensor where you have a suspended wire between two contact points. This is transient line source. This is a new method that we've added to this to the MP-1. Of course, we make the TLS 100, and we've had that method for several years. So really bringing this together in the MP-1 was a valuable and easy addition. So both of these are available, and then but what we're going to talk about is the third method is the transient plane source, or the TPS. So before we move into showing sample setup, the MP-1 itself, what makes it quite unique is that it has a 4-channel switch that allows you to connect 4 devices or 4 sensors into the same controller. So every controller comes with a port in the front and 3 ports in the back. So we have it configured now with a transient plane source, or TPS, temperature platform. Temperature platform is a proprietary heating and cooling device. This particular one goes from 0 to 300 Celsius. It's thermoelectric controlled, but all of the heating and cooling is inside this convenient module. And this is the temperature option on the transient hot wire, or the THW TP. Again, with back pressure you can test up to high points. This comes in both of these come in as low as cryogenic temperatures up to 300 Celsius. So both of these can be controlled by the same controller, so they can be connected. Of course, any arrangement of all the above. So typically the port 1 in the front is used for your benchtop measurements in whichever method you're looking at, or you can combine several benchtop measurements. Let's say you had 4 TPS sample holders, you can measure all 4 with the same controller, and that's built in that expansion. And any of these methods and or temperature devices that are associated with them can be added at a later point, just depending on your needs. So we're going to change camera and just show a basic setup of a sample by a transient plane source. So here is our room temperature sample holder. This adapter, which we're going to use to connect the sensor to the cabling, is good to about 60 Celsius, but this can be upgraded to 300 Celsius. So that would be as if you wanted to use this sample holder inside your own oven, you can. The sample holder is good for 700 degrees. It's the adapter that needs to be upgraded. So what we're going to do is, this is the transient plane source sensor. This is model 33171, which is 12.8 millimeters diameter. This has 4 contact points that we're going to make electrically with the adapter, which connects it electrically. We're going to put those face down, and in the front of our adapter there's a slot. I'm going to start this, and this makes for easy setup. It's a little difficult when you're trying to do it with camera, and then I'm going to just lift the camera so you can see why this is unique. So there's a window there, and that window tells us that the sensor is fully inserted. Hopefully you can see that. That makes, when we have it fully, the window and the back of the sensor fully exposed, we know we've made contact. And then there's a screw that lowers a plate and completes the 4 contacts. And that makes for a very robust, you only need that finger tight, makes for a very robust electrical setup for the sensor. So if we want to make, the types of measurements we're going to make today are symmetric, meaning 2-sided. But if you wanted to do single-sided, this same setup can be used for asymmetric or single-sided setup. So if you want to do a single-sided setup, this is a piece of XPS, which is known. We know the thermal properties of it, and that becomes part of the calculation. If you want to have different thickness of samples for single-sided or 2-sided, you can raise and lower the sensor with the adapter. So that's how we handle change in height of the sample. You can just affix it. So your setup for asymmetric would be like that. You would lower everything. It'd be basically the same, just with this difference for single-sided setup. But we're going to do a asymmetric setup, or sorry, symmetric setup. So the samples we're going to measure or set up are stainless steel. So we'll put a piece on the bottom, piece on top, and we're introducing this just to make sure we don't scar or damage the top side of our second piece. We're going to macro adjust by lowering the top bar. This has clip-in ports that make sure we don't get any movement of this bar over time, with either by temperature, and you can apply quite a bit of force because there's no drag. It locks them in, and to release them, you just pull on it. And then we do just fine adjustments with the knurled knob. And you only need finger tight for non-compressible materials. If you're measuring compressible materials, you of course measure that with a force gauge, or take this top bar off and use a weight, or for more sophistication, we have a compression stand. So that's our setup for stainless steel. I'm going to move to the software in a moment, but before I do, we've set up, previous to the demonstration, on the other channel, which is port 4, we've set up Pyrus RAM 9606. So it's the same setup, it's just a different sample. And this lets us run a schedule and have an average of 5 measurements already prepared to show you in the software, just to save time in demonstration. But we're going to go through all the steps on stainless steel so you can see that. So I'm going to switch to the screen. So you should see, so we've separated the software into 2 applications. First one being data acquisition, which controls the acquisition of data by the name, as well as all the channels and all the scheduling of measurements with methods. We're going to walk through that. The second application is analysis, which takes our data, we can import it and do calculations, whether it be easy or sophisticated. Why we did that is it allows us to have a much cleaner set of software used to control the MP-1, and really maximize and develop them both independently so that the user has more information access and more tools. So this is our initial screen. Here we would point to where we want the data saved. It's saved in sequence to each other. We are using a 3D source, 3D disk source, or TPS. There are other methods, such as transient hot wire, which is what we have set up on the temperature platform. You can see over here that I previously scheduled a measurement as well, which is complete. We have the needle, but today we'll just be looking at the TPS. Within the TPS, we have 2 approaches. One is 1-dimensional and 3-dimensional. We'll be doing a 3-dimensional test. Again, we're doing symmetric, not asymmetric, single-sided. These are the other modules that you can use in addition to your three-dimensional, such as anisotropic for measuring directional properties, slab for measuring thin conductive sheets. We have a thin film module for looking at coatings, freestanding films, as well as some other modules that are buried inside of the 1D module, which we'll talk about in another demonstration. So we go to devices. So before we go to devices, you can click this home button, and this shows you what is connected to your MP-1. This is it is self-identifying the devices that are connected to it. So as you'll see when we go to the next screen, this is not a drop-down list of options because we embedded them there. They are self-detecting. So it knows it has a room temperature sample holder connected to it. So when we go to our next screen, it detects the model of the controller, the serial number of the controller, as well as a room temperature sensor, which there's two, but they're duplicates of each other, just on two different channels. This is the transient plane source TP, a transient hot wire TP. So we're going to run room temperature. And here's where we can input the name of the sample. The height of this sample is 21 millimeters in height, and the diameter is 20 millimeters radius. We're going to select the port that stainless steel sample holder is plugged into, so it self-identifies these. So it's the room temperature sample holder in port 1, and again, that's on the front of the unit. So here we can manually select the sensor because there is an approach to ideally picking the right sensor, but because you entered the height and the radius, we can just click the sensor recommendation. Of course, it pops up 33171. I of course selected and already installed 33171 in the setup, but if you didn't know what it was, you might enter this and go and set the sample up based off the dimensions of your sample. Of course, there are manual ways of calculating this. It's pretty easy. Because we don't want to waste any time if the electrical connection to the sensor is not made, we have a check for that stage. Here we press check sensor resistance, and it will verify that the sensor that you selected from above is valid based off the resistance, its known resistance, as well as if you have an open circuit or closed circuit, it would tell you that. And if you mouse over it, it gives you the ohms. Temperature is automatic unless you want to manually enter it. The temperature, there is a temperature sensor inside the adapter. Again, the adapter, that's the basic one, is up to 60 degrees. And then there's a higher temperature one up to 300 degrees, but it automatically records the temperature. From here, you can manually select power and time. There are guides to help users determine what test time and power to use to achieve a minimum temperature rise, for power and test time to achieve a certain amount of penetration. But we developed the ITPS, which is an intelligent, and that's really key motivation for the MP-1, is to make this system intelligent. So the ITPS, what it does, it allows you to pick groups of thermal conductivity range wherever your materials may be. And if you pick low and your material is very high, it will walk through the different stages until it reaches the temperature rise that your material should have based off the sensor you have, as well as the penetration depth. So why does it know the penetration depth? Because this system measures thermal diffusivity, and you already input the dimensions. So what it's going to do, it makes a continuous measurement until it's reached those parameters. And it has a clever, intelligent algorithm to enable automation of selection of power and test time, although you can still do it manually. So at this point, I'm going to click the ITPS, and it'll open up a screen, and it'll start doing some basic measurements and walk through that. But while it's doing that, we'll switch to our analysis application and review some data. One more thing to point out, because there's 4 ports, we can add repetitions of the same experiment across 4 ports. If I had various of a similar type of sample setup, we could add different ports channels. So stainless steel would fall into actually it just falls on the edge of medium or high. We're going to pick medium because it fits. We're going to click the ITPS, a splash screen comes up, and there'll be some progress on this, which we'll come back and visit. So here we're going to go to the second application, which is for analyzing data. So you would import this data. Here's 5 measurements on that same Pyres RAM. We ran the ITPS parameter optimization, and it suggested 4 seconds based off the available penetration depth between the edge of the sensor and the edge of the sample. It does give a very precise power versus a user might just say 200 milliwatts, but that's what happens when you automate. You can get a more precise power. If we group them all by just selecting Shift, we can see all the data, which is our transient versus time, so temperature rise versus time. This is our drift, so we're in a room right now. We want to make sure that our room is isothermal, free of temperature drift. If you were inside one of the temperature platforms or an oven, we would want the same stabilization. So in advance of every measurement, it records 40 seconds worth of stabilization data points. Our residuals, which confirm that we have a good fitting into the model, this should be nice and random and free of 2 things. Free of the front end of the data, which would be contact resistance between the sensor and the sample, and on the back end of the data, free of hitting the edge of the sample and bouncing back, which would be reflections. These are the default calculations, and the reason why we haven't had to do any additional is because of two main technologies. One is we have the ability to calculate contact resistance between the sensor and the sample. So because we know the contact resistance between the sensor and the sample with every measurement, we know when the heat is diffusing inside the body of the sample. So we're able to remove that portion of time automatically, and that's what we call contact correction. And the reason why we don't have reflections is because the time has already been adjusted based off the available probing depth on the samples, rather the dimensions we included. But another capability of the transient analysis app is really the ability to add more calculations. So you're not editing the same calculations, you're adding new calculations to the same set of experiments. So let's just say we want to add a new calculation, and another key advantage of the MP-1 is the frequency of points. So we're actually collecting data points of about 400 points. So it's at a much higher rate than what's available on the market. So if we switch our recording of points from time to points, so we can switch both of them to points or back to time, but we're going to switch to points, and then include all the points and turn off contact correction. And this is what you would do if you wanted to manually remove the contact resistance between the sensor and sample. So I'm going to calculate. This will take a moment because there's 5 measurements. As you can see, I have my existing transients, which has good fitting, and the time, you can see that from this blue line, the portion of time that it automatically removed. And with our second calculation, we remove that, and you can see that now we have a temperature rise due to contact resistance, which we can manually remove if we want to, and then edit that calculation, the one that's highlighted. You see that it removed a portion of time, recalculate. And we can compare the results from the manual removal to the contact. So here, if we go to results, you can see the average of conductivity, diffusivity, and volumetric specific heat, and the repeatability. And if we look at that second set of calculated results, it's very comparable. So what's really interesting is if you have, and here we have our thermal conductivity on the transient hot wire that we measured at 40 degrees inside the temperature platform. We can look at data across different methods, all within the same analysis software. So you can apply, let's say we had several temperatures by TPS. We can apply, if we want to push, if we had second sets of data, we could push calculations to various spots. And if I had a lot of data and I want that data to be highlighted, I can mark them as important, and then it stands out. So all of this data can be exported to Excel, and really gives you maximum, and it records everything within a nice efficient package within Excel. So that's the analysis app. There's really quite a bit more you can do, but that gives a little summary. If we go back to the application for data analysis, you can see that it tried it ran the ITPS, and it recommended a test time of 10 seconds and 1,000 milliwatts. And if I hit close, it dumps those parameters into the recommended power and time. Here we could run a quick transient if we wanted to, just to look at early results, or we can go to the next screen, which lets us run a schedule. So here we can add a step, we can delete a step. So let's say, and here's the parameters from the ITPS from above. So we can put in the power that it suggested. We can also, if we wanted to vary the parameters, if we didn't run the IPTPS or we wanted to see how parameters affect measurements, this is a multi-scheduled tool that lets you select a power range by a power increment or all the different times. So it's a really sharp way of doing various parameters. And if I was running one of the temperature devices, you would see the ability to add temperature steps to this. So here we're going to run 5 measurements with a 10-minute delay. That, of course, could be 5 minutes. And we're going to hit start. And now that schedule is part of what we just created, is part of a sequence of schedules that the other two are already done. So you can see from PyRSRAM, these are the measurements. You have an event log and your data. So there is, you see results within the data acquisition, but the analysis app gives you full capability. And you can just shortcut to the analysis app. Here you can see the spread of the data. It's basically 4.04 at a temperature range of 0.7 to 24.8. And here you can see the same for the liquids, which was water rather. And that is basically a demonstration, just showing the two software packages and some summary of data. Any questions? Is there any questions in the comment box? I can verbally answer them now if there's any. Please feel free. Oh, thanks, Sophia. This a lot of this is your work, of course. Of course, if there's no questions right now, you can always contact us for via info@thermtest, and we'll answer any questions directly. So if there's no questions right now, this is our first take at live demonstrations. I think we're all done. Thanks for attending, and we'll be having more of these. We're going to try to do them at a pretty frequent number of times and cover different things. Thanks so much.